All right, welcome to another podcast. In this episode, we're going to be taking a look at alternating series, as well as we're going to get into the root test and ratio test. As you might be able to tell, my voice is a little off today, a little bit under the weather, but hopefully you'll be able to hear this just fine. This lecture is a makeup lecture that you'll be working on this weekend, and then looking at the associated bonus quiz. Now, for alternating series, we're going to start with the definition. The definition of an alternating series is that if you have a sum from 1 to infinity, and an is the general term, then this sum is said to be alternating if an takes on one of two different forms. So either you can write an as minus 1 to the n bn, or you can write it in the form minus 1 to the n plus 1 bn, where the bn terms are positive. So a series is alternating essentially if you see either one of these two terms as a part of the series. And I can have other powers besides n and n plus 1, but those are the typical powers that we use. So here's an example. And in some ways, this is the most important example. Consider the sum, n goes from 1 to infinity, of minus 1 to the n plus 1 over n. So here, an would be the entire term, and bn would be just the 1 over n. It's the part of the term that doesn't alternate, whereas an is the entire thing. Let me write down a couple of terms of this sum so we can get a little bit more familiar with it. So this is the sum 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 and so on. If you're thinking that looks very familiar, it's basically the harmonic series, right? The harmonic series is 1 over n, except we're alternating between plus and minus on each of the terms. Similarly, I could define this as minus 1 to the n over n, in which case the first term would be negative, and then we would alternate positive and minus from there. So it would be slightly different than the sum above, but they're going to have very similar convergence properties. This sum is called, in either form, it's called the alternating harmonic series. Now, we know from experience that the harmonic series diverges, so it's going to be interesting to determine whether this series will diverge as well. Now, in order to determine the convergence or divergence, let's say, of a alternating series, we're going to use something called the alternating series test. So let me explain the alternating series test. Typically, I will abbreviate some of these tests, and so if you see me say AST, that's the alternating series test. Okay, so the alternating series test basically starts off supposing that you have an alternating series. So suppose that the sum of an is alternating. Then, if the first thing that has to be true is that the limit of the bn's, remember the bn's are the piece here, the part of the sum that's not alternating, if the limit of the bn's is equal to 0, and the bn is a decreasing sequence, then these two things combined is enough to tell you that the sum converges. Well, that's actually really useful, really helpful. It's actually not all that too difficult. All we have to do is confirm that the non-alternating part of the series is going to 0. The terms are going to 0. And we have to also confirm that the terms are decreasing. All right, so notice that this is going to have really interesting implications when I try to apply it back to the alternating harmonic series. For example, if I revisit this alternating harmonic series, we know that the Bn for this series is 1 over n. And so if I'm checking the two hypotheses that I need for the alternating series test, the first thing is, can I show that the limit as n goes to infinity of 1 over n is equal to 0? Well, that's certainly true. And the other thing I need to check is, does this sequence, is it a decreasing sequence? You can clearly see that, but remember, one of the ways that we can check to see if a sequence is decreasing is by thinking about the value of an plus 1 minus an. That should be less than 0 if it's decreasing. An plus 1 is 1 over n plus 1. So in this case, it would be bn plus 1 and bn. 1 over n plus 1 minus 1 over n. Is that less than 0? Well, that is the same thing if I get a common denominator here. That's the same thing as n minus n plus 1 over n times n plus 1, which is minus 1 over n plus 1, and clearly that is less than 0. So, put a check mark by this. This series is, or this sequence, excuse me, is definitely decreasing. So both of those hypotheses are met, which means that this series overall converges by the alternating series test. We have that the terms go to 0, and we have that it's a decreasing sequence. That's really interesting. The reason that's really interesting is because we know that without the alternating, without this minus 1 to the n plus 1 term, the series 1 over n diverges. So this is going to lead us to some new definitions. So here are just some of my remarks about what this little investigation has shown us. The first remark is, if the sum of the absolute value converges, then this is a definition, then the sum converges absolutely. So if you take a sum and then you take the absolute value of its terms, and that series converges, then the original sum, which could be alternating, will converge what's called absolutely. The example here is that the harmonic series, the alternating harmonic series, doesn't have this property because even though the alternating harmonic series converges, as we've shown, if you take the absolute value of its terms, the absolute value of its terms is just bn because you get rid of this alternating piece, and we know that that series diverges. And here's basically that definition. If you know that the sum converges, and you know that when you take its absolute value, that series diverges, then the original sum is said to converge conditionally. So the point that I want to make here is this alternating harmonic series is a conditionally convergent series because this converges, but when I take the absolute value of the terms, they will no longer alternate plus minus. You'll just get 1 over n, you'll just get the bn back, and this series diverges. So since the original series converges, but the absolute value series diverges, then that's an example of what's called conditional convergence, or it converges conditionally. Contrast that with absolute convergence, which is a much stronger form of convergence. Absolute convergence is when not only the alternating series converges, but so does its absolute value series. So I'm thinking of this as being the alternating series, and I'm thinking of this as being its absolute value series. So when the absolute value series converges, then the alternating series will also converge, and that's a stronger type of convergence called absolute convergence. All right, so now that we have some examples of what it means to be absolutely convergent versus conditionally convergent, I want to take a look at a couple more examples. The example that we said before was sort of the poster child for conditionally convergent was this alternating harmonic series. So this series was conditionally convergent. What can we say about this series? So say we looked at the series, n goes from 1 to infinity, minus 1 to the n over, let's say, something like n squared. Well, in the case of this series, the part that's not alternating is 1 over n squared, and you can clearly see here that the limit as n goes to infinity of 1 over n squared is indeed 0. This is a decreasing sequence. So both of these two things combined tell me that this sequence converges by the alternating series test. So I know in this form, I know that the sum of an converges. Right? That's what I just figured out. What I need to now figure out and do a little bit more with is, does the absolute value series converge? And so the absolute value series if this is an, then I'm going to compare this with looking at the absolute value of that series, the absolute value of the terms. But this is the same as the series n goes from 1 to infinity of 1 over n squared. And the point of this is we know that this is a p series with p equal to 2, which is greater than 1, which means that I know this series converges. So not only do I have the original alternating series converging, but I also have the absolute value series converging. And when both of those things happen together, then the original series is said to converge absolutely. So I can say that this converges absolutely. So this is kind of how these two definitions are used. Conditional convergence, the primary example there is the alternating harmonic series. And for absolute convergence, you can think of this alternating p series for p greater than 1 as being an example of a series which is absolutely convergent. Now, a lot of the convergence tests that are going to be coming up after this are going to have, as a result of the convergence test, that if the series converges, then it will converge absolutely. And I just want to make sure that we focus on this definition, because when you're told the series converges absolutely, that means not only does the alternating series converge, but the absolute value series converges as well. And so this is sometimes called strong convergence, whereas conditional convergence is sometimes called weak convergence. Obviously, no convergence would be the weakest form. It would be diverging at that point. But if the alternating series converges, but its absolute value series diverges, then you get conditional convergence. And that's somewhere between divergence and actual absolute convergence. These are really important definitions. Your ability to understand these definitions is going to take you a long way through the material in section 10.6 dealing with the ratio, the root test, things like that. All right, let's try one more example dealing with alternating series, and then we're going to look at something called the alternating series estimation test. So the example that I have in mind is for us to look at the sum, n goes from 1 to infinity, of minus 1 to the n squared over n squared plus n. So in this form, Bn would be the sum n squared over n squared plus n. And we need to check if it's positive and decreasing. So Bn is clearly positive. You can see here that since n is a value between 1 and infinity, then every one of these terms is positive. So the series as a whole is positive. That's good. What happens when I take the limit as n goes to infinity of the bn's? Well, if you recall, this is a rational function, and the limits at infinity of rational functions, if the degree of the top is same as the degree of the bottom, is the ratio of the leading coefficients. Here the coefficients are 1 and 1 in both the top and bottom. And so this limit is 1, which means it's not equal to 0. So alternating series test does not apply. I can't use the alternating series test to determine whether this alternating series converges or diverges, because the terms don't go to 0. Now here's the thing. If the terms don't go to 0, then that gives us an idea for an even better test to try. I'm going to try the divergence test. So when the alternating series test fails to give you an answer because one of the two terms isn't met, you should always try the divergence test next. So for example, the divergence test says look at the limit of the terms of the sum. In this case, that's the limit as n goes to infinity of the whole term here, which is this. And because bn goes to 1, then the entire term is either going to go to 1 or to negative 1, right? Since the limit of just this part, right, just this part has a limit of 1, and this part alternates between plus and minus 1, then the limit as a whole is going to alternate between plus or minus 1. And the point to make here is there is no limit, so no limit exists. So the conclusion then for the divergence test is the terms of the series have to be going to 0 in order for the series to converge. And so if the terms don't go to 0 or the limit of the terms doesn't exist at infinity, then the series fails the divergence test. So this series will diverge by the divergence test. So don't assume that just because you're working with an alternating series that alternating series will always converge, because there's some alternating series that don't converge, and typically when they don't converge, it's because of them not passing the divergence test to begin with. All right. All of this looking at alternating series kind of has me wondering a little bit about the partial sums for an alternating series. So the question that I kind of want to pose here is, what do the partial sums of an alternating series look like? What's going on? Well, suppose that S is the sum of some alternating series, and I'll make it a series of the form minus 1 to the n times, let's say, bn. Consider a line, like a number line, where the sum here is S. So this is the value, so I'm saying that this series converges, okay? So suppose we found that this series converged by the alternating series test, and it has some sum S. We don't know what the sum is, but if it does have a sum, if it does converge to some value, we're going to assume it's S. What happens as you take partial sums? So let's say you find the first term of the sum, S1, and it ends up here. Because this is an alternating series, this was below the sum, the next alternating series the next partial sum must get closer to S, hence converging, which means it's going to get closer to S, but it's alternating, so it's going to end up on the other side of S. So like say S2 is here. And the reason that this is important is, suppose there's some small interval about S that we feel really good as our estimation. So this is a good zone in which we can estimate the value of S. So usually we say something like S minus some value, S plus some value, where epsilon is the allowed error. So we want to approximate our sum S to some tolerance, to some allowed error, and to do that we have to get inside this interval about S. Well, what's interesting about an alternating series is we're always guaranteed to be able to do this because if the series converges. And what's interesting is we will get inside progressively closer, but we'll be approaching it from both sides. So say, for instance, S3 is here, still not inside the interval. S4 is here, close, but still not inside. And then now we get to S5, and all of a sudden S5 is inside the allowed interval. The idea being there that there's some value of n for which the sum is in between these consecutive partial sums, and the difference between the sum and the partial sum is less than this value epsilon that I'm interested in. So the idea is, as I go further out in the partial sum sequence, I can get closer and closer to the real sum, but I do it in a way that's alternating, which means that the S is in between two consecutive partial sums, always. I'm not converging to S strictly from above. I'm not converging to S strictly from below. The picture is kind of like this. Let's suppose that my sum S is right here. Then I'm converging to that sum from below, but I'm also converging to that sum from above every other term. And so I'm kind of ping-ponging back and forth, but closing down toward the sum. This is a very interesting property of alternating series, and the reason it's interesting is it's going to allow us to specify a value of epsilon and then figure out or determine a value of n that lets me get within epsilon of the actual sum. All right, so the question at this point then is, how do we estimate the actual error involved in our approximation to an alternating series? So this is something called the alternating series estimation theorem. And it basically starts off like this. Suppose that we have a sum, it's an alternating sum of the form an, which means really it's of the form minus 1 to the n times some bn, which converges based on the alternating series test. So we have a convergent alternating series. And I'm going to let Rn be the error of the estimation S minus Sn. In other words, this is the actual value. This is our estimate. And so how far off the actual value you are based on your estimate is the error. And here's what the alternating series estimation theorem says. The size of this error is less than or equal to the next term in the sequence. So this is the next term in the sequence. Now, if you're wanting a reason for that, let me go back to this illustration that I made just a second ago. You've got the sum S here in the middle. Eventually, let's say Sn is right here. I know that Sn plus 1, right? Sn plus 1 is going to take me over to the other side, right? Well, what do you add to get from Sn to Sn plus 1? So this distance here to get to Sn plus 1, this is literally Bn plus 1. But the error here, the Rn, is the distance between S and Sn. That error, this distance, is smaller than the distance to the next partial sum. And the next partial sum is Bn plus 1 away, so the error is less than Bn plus 1. That's where this alternating series estimation theorem is coming from. All right, let's see if we can apply an example. I want to look at the sum, n goes from 1 to infinity, of minus 1 to the n over n factorial. And I want to approximate this sum correct to 3 decimal places. Now, I will tell you before we get started that this is a sum which by the end of the semester, you'll actually have a different way of figuring out its actual sum value. But I will tell you that for today, the actual value of this sum is actually a pretty nice value. It turns out to be 1 over e minus 1, which is approximately negative 0.632120. What I want to do is I want you to tell me, I want you to find n so that Sn is equal to negative 0.632, meaning it's correct to 3 decimal places. All right, so the way that we do that is we concentrate on figuring out when our error will not affect the 3rd decimal place. And we can do this by looking at values of the terms of the sum, the bn's, until I get to one that doesn't affect the 3rd decimal place. And when I get to that, I look at the partial sum that's 1 less than that. See, bn plus 1 less than that is n. So I'm just going to list out a couple of these. If I look at b4, b4 would be 1 over 4 factorial. 1 over 4 factorial is 0.0416. Repeating, clearly that's going to affect the 2nd and 3rd decimal places. b5 is 1 over 5 factorial. Still not good enough. b6 is 1 over 6 factorial. Still not good enough. b7, 1 over 7 factorial. This one's getting close. This one is getting really close. Notice that it could affect, if you had a round-up situation, you could round up and affect the 3rd decimal place. So I'm going to go one more to b8. b8 is 1 over 8 factorial, which, let's see here, 1 over 8 factorial is 0.0, so there's 4 zeros here. 248. So there's no way for the 3rd decimal place to be affected, which means that I know my partial sum is accurate to 3 decimal places once I hit the 7th term of my partial sum, because b8 is here, and so the error is created by s minus s 1 less s7. So s7 will be accurate to within 3 decimal places. All right, so let's check that. S7 is negative 1 plus 1/2 minus 1/6 plus 1/24 minus 1/20 1/120 plus 1/720 minus 1/5040. Okay, you add all of those up. This is negative 0.63214. Once again, you can see that that is correct. Agrees with the actual sum, correct to 3 decimal places. Now, what's interesting about this is we know that the error associated with this sum is R7, which is less than or equal to B8. And B8 is this number we have over here. Very, very small error associated with this partial sum. But this allows us to create a range of values that the sum might take on. We know, for instance, that the sum has to be less than or equal to S7. Right? So the sum has to be less than or equal to S7 plus R7. And the sum has to be greater than or equal to S7 minus R7. So this is going back to this picture. You're within Rn either way. So that's basically what you're looking at here. I have the values of R7 and S7 now. If I compute these on either side, this puts the interval at 0.632164. And on the high side, negative 0.632115. So you can see here that even in this interval that I'm looking at, I know I'm correct to 3 decimal places because S is trapped between 2 numbers whose third decimal place doesn't change. In fact, I am correct with S7 up to 4 decimal places. So 0.6321 is correct up to 4 decimal places, and you can see right here that that is indeed the case. So this is using the fact that the series terms are alternating allows you to come up with really good, really strong estimates of an approximation to the actual sum. Now I'll say that this was a little bit contrived in that I calculated each of these values until I got one that didn't affect the third decimal place. Realistically, you would solve for the value of n. So I would try to solve, for example, Bn in this case is 1 over n factorial. I would try to solve for Bn equal 1 over n factorial. I want that to be less than some number. So maybe something like that. The problem is when you involve the factorial into a problem, you can't algebraically solve for what n would be to satisfy this. So you do have to check until you get a value that's inside the error that you want it to be. All right, you're going to look at a couple of examples of these in the study guide as well as in the textbook, and I just wanted you to be aware of kind of how the alternating series estimation theorem works. All right, this is the last little bit that we're going to be doing with this topic. I want to take a look at 2 tests that you can use to determine the convergence or divergence of an alternating series. In fact, both these tests work for series that aren't alternating, but they're especially useful for looking at alternating series. The first is the ratio test. So let me describe briefly here what the ratio test involves. I have several videos over this topic, but I wanted to go through it kind of step by step here with you today. So let's let the sum of an be a series that has the property that when you look at the limit of the ratio of its terms, so the ratio of consecutive terms in absolute value, that ratio is some number L. Then, depending on what L is, we get different results. So the first possibility is if L is less than 1, then the series converges absolutely. And so that's a very strong result. That means that not only does the original series converge, but that its absolute value series will converge as well. All right. if L is greater than 1 or L is equal to infinity or limit doesn't exist, then the series diverges. And then finally, the last thing here is if that limit is 1, equal to 1, then the test is inconclusive. It's not going to be able to tell me for certain whether the series converges or diverges. Now, I want to give you an example that we've already looked at once in this lecture, but it's an important example to revisit, and that's the alternating harmonic series. We already know that this converges by the alternating series test. What does the ratio test have to say? Well, the ratio test would look at the limit as n goes to infinity of the ratio here being minus 1 to the n plus 1 over n plus 1. So this is your a n plus 1 term. And then we're going to multiply by, or divide by an, which is the same as multiplying by 1 over an. So if you take an and flip it, you'll get n over minus 1 to the n. This is 1 over an. So this is generally how you'll see me do these calculations. I'm going to take and multiply an plus 1, the term of the sequence plus 1, and then multiply it by the reciprocal of the an, the term that you see. Okay, this is just the limit as n goes to infinity. If I clean up some of the values in here, you can take and cancel these two, leaving a minus 1 here, in which case you'll end up with minus 1 in the numerator, and then you have n plus 1 to go along with it. So what is the limit of this term? Well, the absolute values are going to take care of that pesky negative, so we're going to get n over n plus 1. The limit of this is 1. So by the ratio test, since the limit was 1, the test is inconclusive. So the ratio test was inconclusive. And the reason that I wanted to show you this is when the ratio test is inconclusive, it is oftentimes related to the harmonic series or something that acts like the harmonic series. So even in its alternating form, we know that the alternating harmonic series converges, but it's conditionally convergent. So a lot of times when you get the test as inconclusive, it's for these conditionally convergent series. Now that's not always the case, but sometimes that's usually the case why the ratio test will fail. All right, I want to look at several examples with you. This is in addition to the examples that are in the videos that you already have access to, but I just thought it would be a good idea to look at several more examples with you. So I'm going to start with the sum. N goes from 1 to infinity of 2 to the n over n factorial. So I'll call this example 1, since really the harmonic series was just kind of a keep going with the harmonic series and show you what that ends up being. All right, so I'm going to apply the ratio test. The ratio test says to take the limit as n goes to infinity of the absolute value of the ratio. So the ratio here would be 2n plus 1 over n factorial, n plus 1 factorial, times, I'm going to flip it, and it's going to be n factorial over 2 to the n. All right, so what does this limit end up being? This is the limit as n goes to infinity of, do we get any cancellations to occur? Yeah, 2n and 2n plus 1 cancel, leaving a 2. N factorial and n plus 1 factorial cancel, leaving an n plus 1. Remember, n factorial is n all the way down to 1. N plus 1 is n plus 1 all the way down to 1. The very first term of n plus 1 factorial is n plus 1. The next term is n factorial and then all the way down. So this is the correct cancellation here, just to demonstrate that to you, since this occurs so often when you do ratio test. This is n times n minus 1 times all the way down to 1. This is n plus 1 times n minus 1 all the way down to 1. And so you can clearly see here that all of this will cancel with all but the first term of this, leaving the n plus 1 that we have here. This is just a little bit of scratch work, but that's exactly what you should be seeing when you cancel factorials like this. All right, that leaves a 2 in the top and an n plus 1 in the bottom. The limit of that as n goes to infinity is 0. 0 is less than 1. So since the limit L was less than 1, this series converges absolutely. Now, it's not an alternating series, so the concept of absolute convergence isn't a big deal here. In fact, it doesn't even apply here because the absolute value series is the same as the series to begin with. But had this been an alternating series, like say for instance I did negative 2 to the n, then I would get that not only does negative 2 to the n over n factorial converge, but so does 2 to the n over n factorial. All right, let's look at another slightly more trickier example. So we'll call this example 2. We're going to look at the sum, n goes from 1 to infinity, of n to the nth power over n factorial. Now, if you apply the ratio test here, then I will be taking the limit as n goes to infinity of the ratio. Here is a little tricky. The n plus 1 term is everywhere I see an n, I've got to change it to an n plus 1. So this is n plus 1 to the n plus 1 divided by n plus 1 factorial. So this is a n plus 1 times 1 over a n. So the reciprocal of this is n factorial n to the n. Now, what's interesting about this is how you're going to cancel these. We're going to start with separating this out a little bit so you can see kind of what's going on here. So I'm going to start with this n plus 1 to the n plus 1 power is really n plus 1 times n plus 1 to the n times n factorial. And then in the bottom, I have n plus 1 factorial times n to the n. And the reason I did that is I wanted you to see some of the cancellations that occur. For example, n plus 1 cancels with the first term of n plus 1, leaving n factorial terms left. But that n factorial will cancel with this n factorial. What that leaves then is the limit as n goes to infinity of, I can drop the absolute value at this point because I know the terms I'm working with are positive, leaves the limit n plus 1 to the n over n to the n. And when you have two powers that are the same power, it's best to combine them into something of the form n plus 1 over n raised to the n. And I'm going to do one more small step here and write this limit as the limit as n goes to infinity. N over n is 1 plus 1 over n raised to the n. Now this is one of those limits that either you know it or you don't. This is not one that you can just kind of figure out by looking at it. It's a really important limit in mathematics. I know when I taught Calculus 1, I would always bring this limit up to students. This is the limit form for the exponential e. So this limit is equal to e, and since e is greater than 1, this series diverges by the ratio test. Now, this limit is so important. Let me write it its sort of full generalized form. If I ask you what is the limit as n goes to infinity of 1 plus r over n to the n, you need to know that that limit is e to the r. It's a really important limit in mathematics, and it's one that you just need to sort of memorize. But it actually ended up showing up in this problem, and it typically shows up when you have functions of this type. Functions that are, see, these aren't power functions and they're not exponentials because the base is raised to the same power as the power is. So these are sort of weird functions that always end up being related somehow to the exponential. All right, that's a small glimpse at ratio tests. We're going to do a couple more examples. All right, let's look at one more example of the ratio test. So this would be example 3. And for this example, I want to do one that's slightly more complicated. We're going to look at the sum from 1 to infinity of 2 to the n factorial cubed over 3n factorial. And really what I want to look at in this problem is how to handle factorials. It's one of the things that students often struggle with when they do the ratio test. So what I want to look at here is the limit as n goes to infinity of an plus 1, which would be 2n plus 1, n plus 1 factorial cubed, divided by 3n plus 1 factorial. Now notice, and this is oftentimes a common mistake, when I plugged in n plus 1 here, I was plugging it in 2n, so this 3 is multiplied by the n plus 1. It's a very common mistake to just write 3n plus 1 instead of this will end up being 3n plus 3. So this is times 3n factorial divided by 2 to the n times n factorial cubed. All right, it's at this point that we want to stop and sort of analyze what possible cancellations that we can make. So 2 to the n will cancel with 2n plus 1, leaving 2. 3n factorial, now this is where it's interesting. 3n factorial here, and this is 3n plus 3 factorial. So when this cancels with this, which terms will it leave? Well, I know I've got a 2 left in the numerator, and I know I've got an n plus 1 factorial cubed. But in the denominator, I've got 3n plus 3 is the first term of that factorial. The next one would be 3n plus 2. The next one would be 3n plus 1. And then the term after that would be 3n. But the 3n from that point down would cancel with the 3n factorial that's here. So the only terms that would survive would be these. Now I also have the n factorial from this piece still left, so n factorial cubed. But this is the sum that I have at this point, or this is the limit that I have. So this is the limit as n goes to infinity of a whole bunch of stuff. This n factorial cubed and n plus 1 factorial cubed, I'm going to get the n plus 1 term survive, but it's going to be cubed. So I have n plus 1 cubed here, and here I have these 3 terms. So in other words, what I'm saying is this and this would cancel, leaving an n plus 1 cubed. Okay, so the final sort of simplified version of this limit is when it's in this form. Now, I want to caution you against trying to FOIL out all of this. Instead, I want to suggest maybe a better way forward, and that is when you look at the numerator of this limit, it's 2n cubed is the highest term plus other stuff, which I don't really care about. If you look at the denominator, in the denominator, the highest term will be if I take 3n times 3n times 3n, which would be 27n cubed, and then other stuff which is lower than n cubed in size. So once again, this is a rational function where the degree of the top equals the degree of the bottom. This is very common when working with ratio tests. You will oftentimes get these rational limits to appear. Here, we know that this limit then is simply the ratio of the leading coefficients, or 2/27. So the limit is 2/27. Since that limit is less than 1, then this series must converge. This series converges by the ratio test. All right, the last test that we want to take a look at now is the root test. And so the root test is the test that you will typically want to use whenever the terms of the series are underneath a root, as the name might imply. It turns out that ratio tests can't help us do everything. That we actually need the root test to help fill in some of the gaps. So the root test begins like this. Let's let the sum of a series be such that when I take the limit of the absolute value of the nth root of the series. So I'm going to take the terms of the series and I'm going to take the nth root of the terms. This is why it's called the root test, because you're taking the nth root of the series. If that limit of the nth root of the series equals L, then we have a couple of cases. The first case is if L is less than 1, the series converges absolutely. If the limit is greater than 1 or equal to infinity, then the series diverges. Now these are the exact same conclusions that we reached in the ratio test. So when L is 1, the test is inconclusive. So the hypothesis for the root test is slightly different than it is for the ratio test, but the conclusions are the same. So let's do an example of this. All right, so the example that I have in mind here is for us to look at the sum, n goes from 1 to infinity, of n to the n over 3 to the 2n plus 1. Now, in its current form, I could definitely use ratio test to do this. However, I'm going to use root test instead so I can show you how root test can simplify some of the problems that you might use ratio test for instead. So I'm going to look at the limit as n goes to infinity of the absolute value of the terms of this series, but I'm going to take the nth root of that. All right, so I want to show what actually happens here when I take the nth root of this expression. We're going to get the limit as n goes to infinity, and the root can come inside the absolute value here. I'm basically multiplying the exponent by 1 over n. So the exponent here is n times 1 over n. That's going to leave me with an exponent of n. Then here in the bottom, you've got 3 to the 2n plus 1, and I'm raising that to the 1n power. That's going to take and divide each term of the exponent by n, so that I'll end up with 3 to the 2 plus 1 over n. Like, this is the effect of taking the nth root. I take the nth root to the top term, the nth root to the bottom term. Now, as n goes to infinity, I get infinity in the top, and I get 3 to the 2 plus 0 in the bottom, which is infinity over 9, or infinity in the limit. Since the limit is infinity, then this series diverges. So this is an example in which we've used the root test to determine that this is indeed a divergent series. Now there are many other examples of tests in your textbook, but the main ones that you're going to want to focus on are alternating series test, divergence test, and the ratio test. Maybe the integral test, but those are the big three: divergence test, alternating series test, and ratio test. And so I hope as you prepare this weekend for this material and for the bonus quiz that those are the three that you'll focus the most on. All right, this is the catch-up lecture, the makeup lecture that I wanted to give over alternating series and convergence tests. And remember that your take-home quiz will be due on Monday if you want to turn it in. All right, thank you for watching.